Alright, so this is part 2 of the gravitation worksheet. In this video, we will solve questions from 11 all through 20. So as we have done in the past, I will display the question before I start solutioning or explaining. So you will have a view of the question that we are discussing. Question number 11. If the mass of the body is doubled, what will happen to its acceleration? So as in previous questions where we have had cases when certain attribute is, let's say, doubled or halved or changed, then I recommend solving such questions by tabulating the way we have done here. Case A, the mass of the body is m and the mass is doubled, which means in case B, we have the mass as 2m. The force remains the same. And if the acceleration was a here, what is the new acceleration for case B? That's what we're going to solve. Now we know that F is equal to m into a. So that gets us what? A is equal to F by m. So here A that we see is equal to F by m. What will be the acceleration here? What will be the acceleration here? It's again given by force by mass. So in this case, it is F by 2m. How much does this come to? This comes to F by m into 1 by 2. And we see that F by m is a. So this is equal to a into 1 by 2, which means the acceleration has halved. So if the mass of a body is doubled, the acceleration becomes half of the original. So this is the answer. A in this case, A dash, let's say, it's a new acceleration, is equal to A by 2. That's it. So question number 12. Well, the question you can see displaying on the board. It says a sheet of paper and a crumbled paper. So basically, we are having two papers. In fact, it's the same paper. It was earlier a sheet like this, and then you crush it, and that's when it is called crumbled. So the question asks us to determine if the two, in the two scenarios, if the papers were dropped, which one would take shorter or which one would take longer to reach the bottom of the container. It's very interesting. If it falls, there is air resistance because of which it takes longer. Again, I repeat, when it falls, if I just drop this piece of paper, it will take longer when it is in this shape as compared to a crumbled piece because there is air resistance. But this is because of air resistance. As far as the mass and the acceleration due to gravity are concerned, and these are the two factors that will determine things. In fact, the mass of the object does not influence the speed with which it falls. Again, I repeat, the mass of the object, and that's because if you recall, the acceleration due to gravity on Earth is given by this formula, g into m by r square, where mass is this is the mass of the Earth and this is the radius of the Earth. You can see that this particular value of g that you can see here, it is independent. This is independent of the mass of the object, and therefore the mass, different masses, will not take different times to cover the same distance. They will take the same distance, and therefore, if we consider air resistance to be 0, this paper or a crumbled paper will take the same time to reach the bottom of the container. Assuming no air resistance, the two will take the same time to reach the bottom of the container. In the second scenario, there is a closed container with all the air pumped out. So there is a vacuum. There is vacuum in this container. In vacuum, the value of acceleration due to gravity is non-existent. It's 0, and therefore there will be no free fall. So in the second case, there is no G and therefore the paper will not fall. This was question number 12. Alright, so for question number 13, as you can read the question, there are 4 planets that we are considering, and a person is visiting all of these, A, B, C and D. These are the various planets, and their radiuses, the radii and their masses compared to that of the Earth are given. So we have considered the mass of Earth to be m and the radius of Earth to be r. So these are our references, and then I have just put this in a tabular form. These are the various planets A, B, C and D. It's given that the mass of planet A is half that of the Earth and its radius is twice that of the Earth, and so on. Mass of planet B is twice that of the Earth, its radius is half that of the Earth. So we have put all the masses and the corresponding radii in terms of the radius of the Earth and in terms of the mass of the Earth. Now, this is the formula by which we calculate the acceleration due to gravity. For Earth, it would be g, which is the universal gravitational constant. Doesn't matter anywhere, everywhere, this value is the same. Here we are calculating the acceleration due to gravity for Earth. So this is mass of the Earth and this is the square of the radius of the Earth. So using this formula with the masses and the radii given, we will find the value of g for all of these planets. So here we go. For A, this value will be g of A, and that will come to g into m is half of m, and the radius will come to square of 2r, so it will be 4r square. So this comes to g into m by 2 into 1 by 4. So r square. So if you organize this, it comes to g into m by r square, g into m by r square into 1 by 8. We know that this is the acceleration due to gravity of Earth, and this is 1 by 8. So here we can write the value of the acceleration due to gravity on planet A. This will come to GE, which is the acceleration due to gravity on Earth, into 1 by 8. So this is 1 by 8 of the acceleration due to gravity on Earth. This is how we determine the value of acceleration due to gravity for planet 8. Similar exercise for the remaining planets will get us the values for the acceleration due to gravity on the respective planets. So let's do this for B now. B. For B, we have g of B will be equal to g. Here mass is twice m and this is half r. So the square of this will be 1 by 4r square. It's the square of this, mind you. So it's 1 by 4r square. Rewriting this in terms of this, we get how much? G into m by r square. This is the value of the acceleration due to gravity on Earth. So we have taken this factors out. We'll see how much the remaining comes to. So this will be 2 by 1 into 4 by 1. So this comes to acceleration due to gravity on Earth multiplied by 8. So this is 8 times the acceleration due to gravity on Earth. Let's now find the value of this quantity on C, on planet C. So let's probably do this quickly for both C and D. So for G of C, this will come to G into m is 1 by 2m and radius is 1 by 2. So when squared, this becomes 1 by 4r square. So this will come to g into m by r square into 1 by 2 into 4 by 1. So this comes to twice of GE. And finally, for G of D, that's acceleration due to gravity on planet D, we have G into M is twice M, and this is twice R. So when squared, this quantity becomes 4R square. So this is equal to G into M by R square into 2 by 4, which is equal to G of E into 1 by 2. So eventually this comes to half of GE. So these are the values of the acceleration due to gravity on the different planets. Now based on this, we have a couple of questions that we will answer. Now we have got all the back-end activity done. When I say back-end activity, we have calculated the acceleration due to gravity for all. So the first question asks, identify the planet in which the highest value of G. So as you can see that this is 8 times G. So the planet with highest G is B. As you can see, it's 8 times a quantity. So this is the planet B, and the planet with least G, the planet with the least value of G is 1 by 8. This is only 1/8. So this is planet A. This is the answer for question number 13. Question number 14. This is a case study. One thing, don't generalize it, but usually I've seen that in physics questions, whenever it comes to a case study, a long passage usually I have seen does not carry a lot of information that you need to solve questions. The questions are anyway based on the physics theory that you will be able to tackle even without reading the case study. So don't generalize this. Make sure that you have the case study at the back of your mind, but go over to the question, check if you are able to answer them even without looking at the case study. If you fall into hurdles or if you come across obstacles, then probably you can go back to the case study and see, but don't generalize it. But this is a usual approach that I suggest. Keep a balance on how much time you are dedicating for reading the case study, because it might not be as useful. That's the overall idea. So let us look at this case study. Let us read it, and then let's answer the questions that follow. What is the SI unit of the acceleration due to gravity? We know that it's meter per second square, which can also be written as meters second to the power minus 2. Is weight a vector quantity? What is weight? We have read this in earlier classes. Weight is the force with which a body is attracted where? Towards the center of the earth. So the direction is known. This is a physical quantity which has direction. Obviously, it has magnitude, 20 Newton, 30 Newton, or whatever. That's magnitude. And because it is directed towards the center of the earth, it is a vector quantity, mind you. It is a vector quantity because it has magnitude as well as direction. Writing the definition of the weight is not a bad idea. You can write the definition of weight. Mass at the pole. That is an object whose mass at the poles is 10 kg. What will be its mass at the equator? Well, this is something that students confuse with. Don't confuse. The mass of an object doesn't change. The weight changes. The mass of the object remains the same, not only on the surface of the earth, but anywhere. If you are, let's say, 50 kgs, then you will be 50 kg even on moon, even on Mars, even on Jupiter. Your weight changes, mind you. The mass doesn't. So the mass will remain 10 kg. Next one, what happens to the value of G as h increases? Now, I think we will try and understand this question comprehensively. I'm talking about a scenario where we are on the surface of the earth and we are at some height above the surface of the earth. Now we know that the value of G is given by G into m by r square. G into m by r square, where r is actually what? R is the distance between the mass and the center of the earth. This is scenario 1. When we are at a certain height, you can see that the distance of this point from the earth, if this is r, then this is r plus So in this case, G will be G into M by R plus square. Doesn't matter how much the value of R in this case, or the distance between the object and the center of the earth is, but it's definitely more than R. And if the denominator has increased, this will definitely decrease. So with increase in height, the value of the acceleration due to gravity will decrease. I repeat here, because the radius, in this case the distance between the object and the center of the earth, has increased, which means the denominator has gone up. So the fraction will come down, and therefore the acceleration due to gravity will decrease. Now let's just look at the last question over here, which is question number 14e. Suppose the gravity, let me erase this so that we have board space to understand the last question, which is 14e. Suppose the gravity of the earth suddenly became zero. If the gravity of the earth suddenly became zero, what would happen to the moon? The poor moon would fall off. I'll tell you how. We're talking about 14e. So when the acceleration due to gravity on the earth becomes zero, so let us understand this. We have the earth in the middle, and the moon is following this path. This is the orbit of the moon. Let's say this is the direction in which the moon is revolving around the earth, and this is earth. Now the centripetal force, what does it decide? I think in part 1, question number 8, we had understood the concept of centripetal and centrifugal force when things are in circular motion. So in this case, centripetal force is what? The earth's attraction, the earth attracting the moon towards it, provides the necessary centripetal force. Now this is in motion, and it's because of the attraction, because of the force of attraction between these two, that the moon is actually able to traverse this path. Now momentarily, if the acceleration due to gravity became zero, now momentarily if the acceleration due to gravity of the earth became zero, then there would be no force of attraction. There would be no force of attraction between the moon and the earth. So the moment this becomes zero, there is no force operating or acting between the two. So at that point, this moon will get thrown away. The moon will get thrown away along the tangent at that point in time when the acceleration to gravity became zero. So momentarily, if there would be no force of attraction between the moon and the earth, and the moon will get thrown off along the tangent. That answers question number 14e. Alright, so we are now on to question number 15. A planet and the planet is X, has a mass 2 times and radius 3 times that of the Earth. So what is the acceleration due to gravity of this planet if g on Earth is 10 meter per second square? So again, our usual data presentation or organization, as I have been insisting, or as I have been suggesting rather. So we have these planets Earth, and X mass of Earth we have taken as m and radius r. So it's given that the mass of this planet is twice that of the Earth, so this becomes 2m. The radius is thrice that of the Earth, and since this is r, this becomes 3r. Now we know that the acceleration due to gravity, it's given. Well, we know it's given. It's 10 meter per second square. And we know that this is the formula to get the acceleration due to gravity of a certain place. So in this case, g into m by r square, that's given as 10 meter per second square. So let us find the acceleration due to gravity of planet X. So in this case, this will be g into mass of this planet, which in this case is twice m, and it's the square of the radius. So this square will become 9r square. So this becomes g into m by r square. We just make sure that we separate the factors that we are familiar with. So g into m into r square is 10 meter per second square. So that's what I have extracted. I've just filtered, call it, whatever word or term we use. It's like bringing that factor out and seeing what the remaining factors are. So in this case, it's 2 by 9. This we know is 10. This is 10. So this will come to 2 by 9 of 10, that is 20 by 9, and that will come to 2.22 meter per second square. So this is the acceleration due to gravity, 2.22. That's going to be the acceleration due to gravity on this planet. So this comes to 10 into 20 by 9, and this will be 2.22 meter per second square. Alright, so for question number 16, a ball is thrown vertically upwards with a velocity 49 meters per second. So in questions like this, don't read the entire question without making notes. You will end up wasting a lot of time, because you'll end up reaching square one without having made any notes. So just keep making note of all the information that we have. Initial velocity is now 49 meters per second. That's the velocity with which this object is thrown. And because the acceleration due to gravity naturally acts downward, but here the ball is being thrown upward, so the direction being opposite, we write this minus here. G is equal to minus 9.8 meter per second square. Before we determine the distance, let's also make note of what the velocity, the final velocity will be. This is inferential. This is not given explicitly in the question, but the fact that it reaches a maximum height. What does this mean? It reaches a maximum height. This language, when it comes to the physics, gravitation and motion problem, it means that its velocity has become zero. It has reached the maximum height, which means it can't get any more. And that's the reason why it's the maximum height. It cannot go any further, which means it has come to a rest there. Momentarily, its velocity has become zero, and now the downward journey will stop. So in this will start. So in this case, the final velocity is zero. Let's see which formula out of these three will help us. In this case, we don't have any mention of time, nor do we have distance here. So we are required to find distance, the maximum height to which this reaches. The maximum height to which it raises is s. In this case, the first one doesn't have any mention of distance. So this is not the appropriate formula. Here we can find distance, but we also need time, and we don't have time. This formula will help us, because this one can find us distance. S is distance, and it has no need for time. So this is the most appropriate formula. Now we know v square minus u square is equal to 2. In case of this, because this is all under the influence of acceleration due to gravity, I'm going to write this as 2 into g into s. Let us substitute the values that we have made note of. So this is 0 minus u will be 49 into 49, and that is equal to 2 into minus 9.8 into s. So that gets us what? S will be equal to, bring every quantity on this side, which gets us to minus 49 into 49 by minus 2 into 9.8. So you will see that this goes 5 times. So this will be 9 into 5 is 45. 245 by 2 meters, and that comes to 122.5 meters. This is the maximum distance to which the ball will reach. That's the maximum it can go. The total time it takes to return to the surface of the earth. So in this case we are talking about, let me just explain this to you diagrammatically. In this case the ball is being thrown from here. So u was 49 meters per second. The ball went all the way over here where its velocity became 0, the final velocity, and we just found this distance as 122.5. Now what are we required to find? The time that this ball takes, or this object takes, to go from here to here and to come back from here to here. So in this case, you know that this time is equal to this time. The upward journey, the time it takes to go all the way from the ground to the top, is exactly equal to the time it takes to come from the top to the bottom. So let us find any t and we will double that. So in this case, we can actually make use of this information as well, this equation rather. So this information will help us for the second part. We know v is equal to u plus at. Let us take the first part of the journey. So in this case, v was 0, u was 49, plus minus of 9.8 into time is what we have got to find. So this gets us 0 is equal to 49 minus 9.8 t. That implies 9.8 t is equal to 49, and therefore t, if you divide this, you get 5 seconds. This is 5 seconds, folks. This is the time that the object takes to go from this position to the top. But here they have asked us to find out the total time for the complete journey. Therefore the total time taken would be 2 into 5 seconds, and that is equal to 10 seconds. So in question number 17, a body is thrown up with a speed of 29.4 meter per second. So as I recommended in the previous question, whenever you're reading these questions, make note of the data, otherwise you will end up wasting quite some time. So here the body is thrown with a speed of this much, and we have got to find its velocity after 1 second. So let us get one thing right, that the body is thrown up. So the acceleration involved is negative, mind you. It is against the natural acceleration due to gravity. The direction of the natural, or the natural direction of the acceleration due to gravity, is downward, and we are throwing the ball against the acceleration due to gravity. So its velocity will keep falling. It started off with 29.4 meters per second, and after 1 second, we don't know how much the velocity is going to be, and that we will calculate. But one thing is for sure, that the velocity will be less than 29.4 meters per second. So which equation of motion helps here? We know v is equal to u plus at, and in here it is v1 that we have taken, 1 for 1 second, the velocity after 1 second. So in this case it is 29.4 plus g is minus 9.8. Where did we get this from? It's not given, so we have assumed the value of g as 9.8 meter per second square, and time is 1. So in this case we can calculate v1. So this is 29.4 minus 9.8. So this comes to 19.6 meters per second is the velocity. So look, we are aligned with what we understood and started off with. We agreed that the velocity after 1 second is going to be less than 29.4. Now they were also asking us to find the velocity after 2 seconds. The velocity after 2 seconds. So in this case, What is the speed and height? So we'll come to the height as well. We'll calculate the height a little later maybe. We'll calculate the velocities after 1 second, after 2 seconds, and after 3 seconds. So in this case, what will be its velocity after 2 seconds? So you will appreciate that the velocity v2 is going to be even less than 19.6 because it is continuously going up against the acceleration due to gravity. So it's dying down, mind you, it's dying down. Its velocity is dying down. Eventually, somewhere, its velocity will become zero, but up until that point, at every moment, its velocity is falling. In this case, if we apply this equation again, v2 is equal to u plus at gets us what? v2 is equal to u, which was 29.4 plus 9.8 into 2. So this comes to 29.4 minus 19.6, and that gets us 9.8 meters per second. We can similarly calculate T3. Now let us very quickly look at how we can find the height. So what will be the height after 1 second? So here we have S is equal to ut plus half at square. We can make use of this formula because in this case we know everything. We have information about u, we have information about t, we have information about a. So let us call this S1. So what is the height that this body has attained after 1 second is what we are going to calculate here. So S1 will be equal to u is 29.4 into 1 plus half into minus 9.8 into 1 square. So this comes to 29.4 plus 1 by 2 into, this becomes minus, and this becomes 9.8. So this is 29.4 minus 4.9. So this gets to 5, 4, 14. Have I made some mistake? Yes, I have. It is 24.5 meters. That's going to be the distance attained by this object after 1 second. If it was thrown with this velocity, after 1 second, it would have risen to this height. We can similarly go for the same, using the same formula. In this case, S2 would be 29.4 ut. In this case, t would be 2 plus 1 by 2 into minus 9.8 into 2 square. So we can find this, we can calculate this, which will come to 58.8 minus 19.6, and this comes to 39.2 meters. You can check for calculation errors if any, but I hope you have got the logic of about how we have approached and solved this problem. So question number 18, a stone is released from the top of a tower of height 19.6 meters. So as we have been hearing, I would say, let us make note of the data that we have in the question. So it's and we have to be familiar with some of the key words here. A stone is dropped or a stone is released. It means it's just left. That's when an object is under free fall. It's released. It's not thrown, mind you, it's just released. So at the time it was just left or released, its initial velocity would be 0, and it is touching the ground eventually, and this point is 19.6 meters above the ground. So this is the building, let's say, and this entire distance is said to be 19.6 meters. It's dropped from the top of this building or it's a tower rather. So if u is 0, we have got to find v. So in this case, we don't know the time. Well, eventually we also have to find time, but up until here, there is no mention of time, so we cannot make use of the second equation of motion, which is s is equal to ut plus half at square. We cannot make use of this formula because we don't have time. Instead, we will use the other equation of motion, v square minus u square is equal to 2 into a into s. Let's try and apply this formula over here. So we know v square minus u square is equal to 2 into g here. G because the acceleration is acceleration due to gravity, which is s. And the fact that this is dropped, this is the direction of motion. So the direction of motion is in the direction of the acceleration due to gravity. So g in this case will be plus 10. So in this case, let us see what all v square minus u square is 0 is equal to 2 into g is given as 10, and distance is what we can find out using this formula. Now the v square, gs is also known, so this is 19.6. So in this case, v square comes to 2 into 10 into 19.6. Over here, this is actually it is actually a mistake, I would say, in the question, that they have given 10 meter per second square as the value. If it had been 9.8 meter per second square, actually we could have found this as a value which would have been a perfect square. Well, not a perfect square, but yes, we could have found the square root rather easily. So for now, you can just substitute 9.8 over here. I would suggest 9.8, and I'll tell you why this helps. Because this also becomes 19.6 into 19.6, that is v square, and therefore v is equal to 19.6 meter per second. Now one disclaimer, call it, well, not a disclaimer, I would rather I would take responsibility. I have, just to make things easier so that I get a perfect square, I have put 9.8 meter per second square instead of this. If you are given this value, don't change this. Find this using 10. You would have to put in some more effort to find the square root of v. That will be some effort, yes, but you should be knowing how to find square root. It will be approximately this velocity, but just make sure that you don't substitute g is equal to 9.8 if it's explicitly given that the value should be 10. In this case, we would have had to find the square root. Well, the second part of the question, we're on question number 18. The second part of the question, how high would the particle rise? Now, sorry, this is question number 18. I was just reading the next one. Also, the second part of this question is the time taken by the ball to reach the highest point. How much is the time taken by the ball to reach the highest point? In fact, I see that we could have taken 9.8 meter per second square without any hassle, because the value of g is equal to 10 meter per second square is given for the second part of the question. So we should be fine. It's the second part of the question. What is the question? The time taken by the ball to reach the highest point. So it's easy now. Time taken to reach the highest point. So we have already got the final velocity. We have got the initial velocity. And we have s. So we should be able to now find t. In fact, we don't need t here. We know we don't need s. In fact, we know v is equal to u plus at, and here we found v to be 19.6, u is 0, and this is 10 into t. That gets us what? 19.6 is equal to 10t, and therefore 10 is equal to 1.96 seconds. So it takes 1.96, approximately 2 seconds for the stone, or was it an object? Yes, it was a stone, to traverse this distance from the time it was released to the time it hit the ground. It was falling down, let me put it that way, for close to 2 seconds. That's the answer. So we are now on to question number 19. A particle is thrown vertically upwards. So let me read this question out. Let us make note of things as we read. A particle is thrown vertically upwards with a velocity of 20 meters per second. A particle is thrown vertically upwards with a velocity of its thrown. So in this case, the initial velocity, which is denoted by the letter u, is equal to 20 meters per second. This is given. What will be its velocity at the highest point of the journey? Now, these are clues. It reaches the highest point. When? When is the point its highest point? When the velocity has become zero. It can't go any more. It can't go any further. And that's the reason we call that the highest point. What happens to the velocity? It dies down. The velocity has become zero. So the final velocity, v, is equal to 0. Yes? What will be its velocity at the highest point of the journey? Now, in this case, the ball is thrown upwards, and therefore you will appreciate that g, which is in the opposite direction to the acceleration due to gravity, and because the direction of motion is upward, will be minus 9.8 meter per second square. So with this much information, we should be able to find v. We know v square minus u square is equal to 2 into g into s. Well, this will not help us here. V square. We can find the distance. Let's find the distance. That's anyway required. So let's find the distance first. V square. So this gets us to 0 square minus 20 square is equal to 2 into minus 9.8 into distance. That gets us, this becomes minus 400 is equal to, well, g is given. G is given. They've asked us to assume 10, so let us use 10 instead of 9.8. It's given. It's given. So we are using minus 10 meter per second. It comes to 2 into 10 into s. Therefore, s, you can see that this minus and this minus get cancelled. So s comes to 400 divided by 20. So 20 meters is the distance. This is answer to question number B, as you can see. How high would the particle rise? So if you can relate this with the practical scenario, a ball was thrown with a certain velocity, and in this case it was 20 meters per second. If the acceleration due to gravity is 10 meters per second, how far would the ball go? And the answer is 20 meters. So it goes to 20 meters. What will be its velocity? We can also find the velocity at the highest point of the journey. Well, this was something that we could have done earlier. What is the velocity at the highest point? The velocity at the highest point is v. That's the final velocity. That's 0. And that's the reason why it has reached the highest point. It cannot go any further, and that's why we call it the highest point. Highest point means it can't go any further. That's the highest it could have reached, and it has reached. So the final velocity at that point becomes 0. So the answer to A is 0. The answer to the second bit is 20 meters. Let's see what the third part is. What time would it take to reach the highest point? Now we know for C, we know V is equal to U plus 80. In this case, V is 0. And this u is equal to 20 minus, mind you, because the ball is thrown vertically upward, so this becomes minus 10. U, it's actually plus of minus 10 into time. So that gets us what? 20 is equal to 10t, and therefore t is equal to 2 seconds. So these are our three answers. I'm just highlighting the three answers. Final velocity 0 meters per second. How high would this particle rise? 20 meters. What time it would take to reach there? 2 seconds. Question number 20. Now in this case, a boy is on a cliff 49 meters high. So the arrangement might look something like this. There is a cliff. This is 49 meters, and there are two stones falling. So the first stone, one, is being dropped, so it's just dropped, and it takes t seconds, let's say, to reach the bottom. The other stone, which is 2, is being thrown, mind you, it's thrown, and it reaches at the same time. This is dropped, this is thrown 1 second later, this is dropped 1 second later, but both the stones hit the bottom together. Mind you, it was thrown 1 second later. So if this takes t seconds, this would obviously take t minus 1 seconds. Now I'll just repeat this scenario, just talk about this scenario one more time. This stone 1 was dropped and it reached the bottom in t seconds. The second one was thrown and they both hit the bottom together, which means even if this was thrown or released a second later, they both hit the bottom together. It means that this stone 2 took 1 second less. And this is what we have. So distance, both of them traverse 49 meters. Stone 1 takes t seconds, so this stone takes t minus 1 seconds. Initial velocity, this was dropped, mind you, this was dropped. So its initial velocity was 0, but this was thrown, so it would have some non-zero initial velocity, and we are required to find this. So in this case, as you can see, S is equal to ut plus half at square is the equation of motion that we can make use of. If we substitute all of these values, and we can assume g as 10 meter per second square, if you solve for this, you get, we can solve this up. 49 is equal to 1 by 2 into 10 into t square. So this comes to what? Well, I think to make sure that this divides properly, let us rather assume the value of g to be 9.8 meter per second square. And you are free to choose. If they don't give you the value of g, you are free to choose the value of g as 9.8 or 10 based on what value helps you. In this case, 9.8 helps me because this is not cancelling. If I take 9.8, it helps. So over here, I get the value of t square is equal to 49 into 2 by 9.8. This is 5 times, and that's the reason why I said it helps to take 9.8. So t square gets to 10. That gets us t, which is square root of 10, and this value is something around 3.1. Now 3.1 is the time that this stone took to reach the bottom. So if this is 3.1, if this is 3.1, t minus 1 would be equal to 2.1 seconds. Now we can make use of this to calculate u1. So in the second case, for stone 2, this was all about stone 1, mind you. This was all about stone 1. Now for stone 2, if we make use of the same formula, we have S is equal to ut plus half into at square. We know S is 49 because even this stone has covered all of this distance. U in this case is u1, so we don't know u1, and that's what we are going to find out. T we found out, 2.1 plus half into g is 9.8 into 2.1 square. So if you solve for this, this is 2.1 u plus this is 4.9. So this will be 4.9 into 4.41, and that gets us how much? 49 is equal to 2.1 u plus, well, let's calculate this, 4.41 into 4.9. It comes to 21.609, 21.61, let's call it approximately. So that gets us how much? 2.1 u will be equal to 49 minus 21. I'm just approximating this value, so it's 28, and therefore u will be 28 by 2.1, which will come to approximately around 15 maybe. You can find the exact answer, but this is somewhere the range. I mean, this is somewhere the approximate value that we can settle for when it comes to this calculation. Mind you, the teacher might want you to solve this accurately, so don't approximate it like the way I have done, but this is not very relevant here. We don't have to spend so much time in this session to find the value of A. This is mere class 6 algebra or calculation rather. So this comes to around 15 meters per second. This is the answer to question number 20.